Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. This lecture 2 is about parallel computing platform part 1. So this lecture will cover only two topic overview, which are implicit parallelism, trends in microprocessor architectures, and limitations of memory system performance. So let's look at the scope of parallelism. Conventional architectures coarsely comprise of three components, which are processor, memory system, and data path. So each of these components has their own significance and limitation. So parallelism addresses each of these components in significant way. So different applications utilize different aspects of parallelism. For example, if you use data, so data intensive applications utilize high aggregate of throughput, and server application utilize high aggregate network bandwidth, and scientific applications typically utilize high processing and memory system performance. So it is important to understand each of these performance bottlenecks, right? Okay, so implicit parallelism trends in microprocessor architectures. Microprocessor clock speeds have posted impressive gains over the past 2 decades, about 2 to 3 orders of magnitude, which means the microprocessor technology becoming mm, better over the years. Higher levels of device integration have made available a large number of transistors. However, it's use large number of transistors. The question of how best to utilize these resources is an important one. So because of that, we need to identify, or we need to find out how to utilize these resources in the best way. So current processors use these resources in multiple functional units and execute multiple instructions in the same cycle. Okay, so the precise manner in which these instructions are selected and executed provides impressive diversity in architectures. So because of we have a difference of application and multiple functional and also multiple instruction are being executed at the same time. So the architectures of microprocessor become diverse and also has different types of uh, architectures and technology being offered by the manufacturer. Okay, so next. So there are two kind of execution in parallelism, which are pipelining and also superscalar. Pipelining overlaps various stages of instruction execution to achieve performance. So if we look at the pipelining, so you need to imagine as a pipeline. So it will overlap various stages, okay, step by step, level by level. So at a high level of abstraction, an instruction can be executed while the next one is being decoded and another next level is being fetched. So at one time, level after the level, so it comprises of many kinds of instruction being executed. Okay, this is similar to an assembly line for manufacturers of cars. So if you can imagine the pipe or how the pipeline is being executed, please imagine manufacturing of cars, whereby to build a car, we need to have different kinds of operations that should be running at the same time. So let's say uh, in the factory, it has a department of building a door only, okay, color the body, installing the engine, and many departments covered different kind of um, body parts of cars. Okay, so however, pipelining has several limitations. So it considers the speed of pipeline is eventually limited by the slower stage. So as we discussed previously, the pipeline consists of several instructions that being executed in at stage by stage. So if one of the stage has the slowest operation or speed, so it will lower down the performance of the pipeline operation. So for this reason, conventional processes rely on very deep pipeline to overcome the limitation of the slower time in pipeline execution. So the manufacturers overcome with by promoting the pipeline in concept of very deep pipeline, which by it offers so many stages of uh, pipelines. Okay, for example, the Pentium processors. However, in typical program traces, every 5 to 6 instruction is a conditional jump. This requires very accurate branch prediction. So let's say we have 20 stages of pipelines instruction. So maybe in the fifth or sixth instruction, there is a conditional jump whereby the instruction need to be skipped to another instruction. No need to follow the step by step because of maybe the instruction depends to another instruction. Maybe that instruction depends on the data that being processed from the previous instruction. So that's why it needs a conditional jump. So the penalty of a misprediction grows with the depth of the pipelines, since a larger number of instructions will have to be flushed. So if wrongly predict the pipeline stage, there are too much stages and many instructions need to be removed caused by the conditional jump. Okay, so one simple way of reducing the limitation of the pipeline is by using the multiple pipeline. So multiple pipelines also being called as superscalar execution. So the question then becomes one of selecting this instruction. So superscalar execution actually in a superscalar computer, the central processing unit or CPU manages multiple instruction pipeline to execute several instructions concurrently during a clock cycle. So this is achieved by feeding the different pipelines through a number of execution units within the processor. So superscalar actually consists of multiple pipelines that being executed concurrently during a clock cycle. Okay. Alright, so this is an example of superscalar execution. As you can see there, we have three different execution. Okay, however, these three execution actually do the same task to add the four numbers and then store the result into a memory. Okay, so this is A, and then if you can see at B, the execution schedule for code fragment in A in 1 here. Okay, so we take one example here. Okay, for the first execution actually load the data R1 and also R2. Then the next one we have add the R1 and also add the R2. Then the step number 5, adding the R1 and R2, and then the result of adding R1 and R2 is stored into R1. So this instruction is being transformed into schedule code fragment. Okay, and then as you can see here, IF is stand for instruction fetch, ID instruction decode, OF is operand fetch. Okay, E is equals to instruction execution, WB is equals to write back, and NA is equals to no action. So this one is the time frame from 0 to 8, right? Okay, So from the schedule, execution schedule, we can transform to the C, which is we want to look at whether the hardware is really being utilized or not. Okay, so taken from time number 4. Okay, at time 4 there is a waste here. Okay, where there is no execution being executed during time 4. Alright, so that's why here, as you can see, the white color is empty issue slot because there is no instruction being executed. There is no any operation being held here. Okay, then we go to step 5. Where is 5 here? Okay, so execution being the instruction being executed. Okay, at the time slot. Okay, full time slot, full issue slots. Yeah. Okay, and then we move to the 6th one. Yeah, 6. Okay, one is instruction execute, and NA there is no action being execute. So that's why time slot for 6 only. One issue being used. Okay, another one is not being used. So how about time number 7? WB, which is equals to write back. Okay, so that's nothing execution or operation being executed. So the issue is there is an empty slot. So actually it's a waste here, right? Okay, let's look at the next one, the explanation of the diagram. So in the above example, there is a some wastage of resources due to the data dependency. Why the slot is not full each time at time 4, 5, 6, and 7 due to the data dependencies. So the example also illustrates that different instruction mixed with identical semantic can take significantly different execution time. So if you can see from the previous diagram, these 3 operation actually hold the same operation, which is adding a numbers. Okay, however, each of these operation takes different number of operations. Sometimes it needs 6 steps, sometimes it needs 5, and sometimes it needs 6 again. So depends on the algorithm, right? Okay. Same goes with the execution time. So if we require more steps of operation, so of course we require more time. Okay. All right. So let's proceed to the next one. Okay. Superscalar execution. Scheduling of instructions is determined by a number of factors. When we want to make a schedule for the instruction to be executed, so we need to consider several factors. Okay, the first factor is through data dependencies. What is meant by this? The result of one operation is an input to the next. It's about data dependency. So let's say stage number 2, when it wants to execute the operation, it needs the data from the uh, operation number 1 or stage number 1. Okay, so it is called as data dependency. So second factor is called resource dependency. This dependency is happen when 2 operations require the same resources. Okay, they need to use the same resources so that the operation can be executed. So factor number 3 is called as branch dependency. So branch dependency is when scheduling instructions across conditional branch statements cannot be done deterministically a priori. Okay, means if the instruction consists of if-else branch, okay, sometimes we cannot predict or we cannot define or cannot schedule the instruction in early stage. Okay, so when the instruction being executed, then we know there is a conditional branch there need to be used. Okay, and then the scheduler, what is meant by scheduler is a piece of hardware looks at a large number of instructions in an instruction queue and selects appropriate number of instructions to execute concurrently based on the three factors that we have discussed. So that is the function of scheduler. It will choose which instruction that can be executed concurrently according to the three factors that has been analyzed. So the complexity of this hardware is an important constraint on superscalar processes, which means when we want to implement superscalar, we need to consider three factors and then will be chosen by the scheduler whether the instruction can be done concurrently or not. Okay, all right. So there are some issues that need to be discussed in superscalar execution. The first one we call as issue mechanism. So there are two issue mechanisms here whereby in order or dynamic. In order actually is a simpler model whereby the instruction can be used only in the order in which they are encountered, which means if the second instruction cannot be issued because it has a data dependency with the first, only one instruction is issued in the cycle. So the second instruction need to be wait for the first instruction to be executed. Okay, so the second mechanism issue is called as aggressive model or named as out of order. Okay, why it is called as aggressive or out of order model? Let's say this if the second instruction has data dependencies with the first, however the third instruction does not have the dependencies, so the first and the third instruction can be co-scheduled. So this is called as dynamic issue. So it can jump to other instruction which has no dependency at all. Okay, so performance of in-order issue is generally limited compared to dynamic issue. Why? It needs to wait for the previous instruction to be executed first, then it can be executed. Okay. So next, another consideration that we need to highlight is called as efficiency. How we want to find whether the superscalar execution is efficient or not. So we need to identify from the several points. Okay. The issue is caused by the functional unit itself, whereby not all functional units can be kept busy at all. So we have some idle time during the parallel process. Okay, so if during a cycle, if there is no functional units are utilized, it is called as vertical waste. And if during a cycle there is some of the functional units are utilized, it is called as horizontal waste. So due to limited parallelism in typical instruction trace dependencies or the inability of the scheduler to extract parallelism, the performance of superscalar processes is eventually limited. Okay. So conventional microprocessors typically support four-way superscalar execution. Okay. So let's look at the next one, which is called very long instruction word processor. All right. This processor actually is one type of superscalar processor. Okay. The hardware cost and complexity of the superscalar scheduler is a major consideration in processor design. So to design the very long instruction word processors, it depends on the hardware cost and also the complexity. So this kind of design actually rely on the compilation time analysis to identify a bundle together instruction that can be executed concurrently. So VLIW will analyze the instructions during the compilation time, and then will identify which instruction can be executed concurrently and bundle it together first. Then it will execute all the instruction that has been bundled or collected together concurrently at the same time. Okay, so these instructions are packed and dispatched together, and thus the name it called as very long instruction word. Why? It packed it together. Okay, consists of so many instruction and then execute at the one time. So this concept was used with some commercial success in the multi-flow trace machine, which is named as circa 1984. Okay, so variants of this concept are employed in the Intel IA64 processor. All right. So let's look at the consideration of VLIW. Issue hardware is more simpler. The compiler has a bigger context from which to select co-scheduled instruction because of it do the analysis during the compilation time. Compilers, however, do not have runtime information such as cache misses. Scheduling is therefore inherently conservative. The branch and memory prediction is difficult to be done. VLIW performance is highly dependent on the compiler. So a number of techniques such as looping, unrolling, speculative execution, branch prediction are critical. Okay, so it's really rely on the compiler to identify whether there is a branch jumping, okay, or speculative execution, okay, and also to predict the the critical instruction. Okay, so typical VIW processes are limited to 4-way to 8-way parallelism. All right. So this slide shows you the limitations of memory system performance. There are some terms that related to memory performance that you need to know. The first one is called memory system, and not processor speed is often the bottleneck for many applications. So when we talk about the uh, application of parallel processing, so we need to consider the memory system, okay, and also actually the speed itself. So memory system performance is largely captured by two parameters. So in this slide, we want to discuss about the memory performance. So we need to uh, use these two terms or parameters to identify whether it is good or not in the performance during the parallel processing execution. Okay, so it is called as latency and also bandwidth. So what is meant by latency? Latency is the time. Okay, it's related to the time. Okay, when it is measured from the issue of a memory request to the time the data is available at the processor. Okay, and the second one is the bandwidth. So bandwidth is the rate at which data can be pumped to the processor by the memory. So latency is about the time, bandwidth is about the rate or the size of the data that we can pump to the processor. Processor. Okay, right. So it is very important to understand the difference between latency and bandwidth. So just now we already discussed latency is time, bandwidth is the rate, okay, the rate of the data. Okay, consider the example of a fire hose. Okay, we have the fire hose here. If the water comes out the hose 2 seconds after the hydrant is turned on, the latency of the system is 2 seconds. Means how much time that we need to wait for the water to comes out from the hose after it being turned on. Okay, so in this case 2 seconds. So once the water starts flowing, if the hydrant delivers water at the rate of 5 gallons per second, so the bandwidth of the system is equal to 5 gallons per second. So 5 gallons actually is the size, is the rate of the water that comes out from the hose. Okay. If you want immediate response from the hydrant, so it is important to reduce the latency. So we need to reduce the 2 seconds just now to have the fast response. So if you want to fight big fires, of course we need to have the high bandwidth of the water. Okay, all right. So another example. Okay, so consider a processor operating at 1 gigahertz or 1 nanosecond clock and connected to a DRAM, a memory, with a latency of 100 nanoseconds without cache. So there is a waiting time of 100 nanosecond when the processor is connected to a DRAM. Okay, assume that the processor has 2 multiply add units and is capable of executing 4 instructions in each cycle of 1 nanosecond. So let's observe the following situation. The peak processor rating is equals to 4 GFLOPS. Okay, since the memory latency is equals to 100 cycles and block size is 1 word, every time a memory request is made, so the processor have to wait 100 cycles before it can process the data. Why 100 seconds? Because just now we have the latency of 100 nanosecond between the processor and also the DRAM. Okay, alright, so next one. On the above architecture, consider the problems of computing a dot product of two vectors. Okay, so a dot product computation performs one multiple add on a single pair of vector elements. For example, each floating point operation requires one data fetch. It follows that the peak speed of this computation is limited to one floating point every 100 nanoseconds, or a speed of 10 mflops, a very small fraction of the peak processor rating. Alright, so how to improve the latency of the memory? So we can use caches. Okay, this is an alternative to reduce the time of waiting. So we can implement caches. Okay, so caches are small and fast memory elements between the processor and DRAM. So this memory acts as a low latency, high bandwidth storage. Okay. If a piece of data is repeatedly used, the effective latency of this memory system can be reduced by the cache. Okay. The fraction of data references satisfied by the cache is called the cache hit ratio of the computation on the system. So cache hit ratio achieved by a code on a memory system often determines its performance. So hit ratio actually will determine the performance of the cache. Alright, for example, we still consider the previous architecture. So in this case, we implement a cache of a size 32 kilobyte with a latency of only 1 nanosecond instead of 100 nanosecond without using cache. Okay, so we use this setup to multiply two matrices A and B of dimension 32 times 32. Okay, this example actually is carefully chosen, so it is enough to be stored into the cache, right? Together with the result of the multiply operation. Okay. Okay. So let's observe the situation. Fetching the two matrices into the cache corresponds to fetch 2k words, which takes approximately 200 nanoseconds. Okay, and then multiplying 2 and multiply n matrices or n by n matrices takes 2 and power of 3 operation. So for this problem, it corresponds to 64k operation, which can be performed in 16k cycles or 16 nanoseconds at 4 instructions per cycle. The total time for the computation is therefore approximately the sum of the time for load or store operation and the time for the computation itself. So it requires 200 nanosecond plus with the 16 nanosecond for the all operation. So this corresponds to a peak computation rates of 64k or 216 or 303 M flops, right? Okay. The impact of caches. Repeated references to the same data item correspond to the temporal locality. So if we keep on repeat using the same data item, so actually it corresponds to the temporal locality. So we can access it as the data many times. Okay, and in the given example, we had O multiplied with n power of 2 data accesses and O multiplied n power of 3 computation. So this asymptotic differences makes the above example particularly desirable for caches. So data reuse is critical for cache performance. So cache always being used if we need to reuse the data, okay, more than one. Okay. Then the cache is so beneficial to the memory performance. Okay, so impact of memory bandwidth. Memory bandwidth is determined by the bandwidth of the memory bus as well as the memory unit. Just now we look at the impact of the latency. So in this case, we want to look at the bandwidth. So bandwidth is related to the memory bus, how much the bus can bring the data to the processor. So memory bandwidth can be improved by increasing the size of the memory blocks. We increase the size. Okay, the underlying system takes L time units, where L is the latency of the system, to deliver B units of data, where B is the block size. Okay, so that is the formula. Okay, so look at the example. So still consider the same setup as before. However, this case has 4 block size. Okay, 4 words instead of 1 word. So the operation is dot product computation. So in this scenario, assume that the vectors are laid out linearly in memory. 8 flops for multiply x can be performed in 200 cycles. This is because a single memory access fetches 4 consecutive words in the vector. Therefore, 2 accessors can fetch 4 elements of each of the vectors. These correspond to a flop every 25 nanoseconds for a peak speed of 40 flops. Okay, so you note that even though we increase the block size from 1 to 4 words, actually it did not change the latency or waiting time of the memory system. However, it increased the bandwidth for 4. So in this case, the increased bandwidth of the memory system enable us to accelerate the dot product algorithm, which has no data reuse at all. Okay. Okay, it is important to note that here we discussed about the bandwidth. If we increase the block size, it does not change the latency of the system. So we need still to have the waiting time. Okay. Physically, the scenario illustrated here can be viewed as a wide data bus, which can bring forwards or 128 bits connected to a multiple memory banks. So there are many memory, okay, that are connected to the bus that will bring the data to the processor. So in practice, such wide buses are expensive to construct. To buy the big bus, okay, are expensive. So in a more practical system, so how we overcome this one? Consecutive words are sent on the memory bus on subsequent bus cycle after the first word is retrieved. Okay. So we overcome by doing the process repeatedly as many times as possible. Okay. Instead of using the large size of buses, okay, it might increase the cost. Okay, so the above examples clearly illustrate how increased the bandwidth result in higher peak computation rates. Okay, the data layouts were assumed to be such that consecutive data words in memory were used by successive instructions, or also known as spatial locality of reference. So if we take a data layout centric view, computations must be reordered to enhance spatial locality of reference. Okay. Okay. So another example, by considering the code fragment. Okay, this code fragment, the sum. Okay, sum of the matrix B, here is the matrix B, into a vector name column sum. The result of the sum columns matrix B will be stored into the vector name column sum. Right. Okay. So the vector column sum actually is a small and easily fits into the cache. The matrix B is accessed in a column order. So where is B here? Can be accessed in column order. The strided access results in a very poor performance. So what is meant by the strided? It is an arranged sequentially in memory so as to be accessed by moving in fixed increments larger than 1. Okay. Multiplying a matrix with a vector. Okay. This is the operation. Okay, let's look at the A and B. A and B have different approach on multiplying a matrix. A multiply a matrix by using column by column, okay, column by column, and B multiply the matrix by computing each element of the result as a dot product of a row of the matrix with the factor. So it has the result here. Okay, result, and result. However, in A, multiply column by column and keep a running sum. Okay, the result is not being written yet. We finish all the column first, then it write the result. Compared to B, after the first row being executed, it will be stored into a result. Okay, until the end. So which operation is more efficient? Okay, so actually it's need more time and large bandwidth. So to overcome this issue, so we adjust the fragment of code by adding another loop. So in this case, the matrix is traversed in a row order and performance can be expected to be significantly better. Okay. All right. So to conclude of the memory system performance, the series of examples have been presented in this section has illustrated that exploiting spatial and temporal locality in application is critical. So how we exploit the data, okay, either spatial or temporal locality approach, okay, is critical to reduce the latency and to increase the bandwidth. Okay, we want to reduce the time, but in the same time, we want to increase the size of the bandwidth. We want to bring more data, but in a smaller time. So the ratio of the number of operations to number of memory accesses is a good indicator to predict tolerance to memory bandwidth. So we need to consider the number of operations, okay, and also the number of memory accesses. If we know this, we can anticipate it, whether the large data can be bring to the processor or not. Okay, memory layouts and organizing computation appropriately actually can make a significant impact on the spatial and temporal locality. So from the previous slide, it shows you from the layout of the memory and also the computation organization also give an impact to the spatial and temporal locality. In this case, on the memory system performance. Okay, so that's all for this lecture. Thank you.